Hello everyone, this is ML Naruto. Welcome to my channel. So today I'm gonna teach you what is the structure of the linear regression models. But before that, uh, let me tell you something. Like for example, I was given some kind of data set. Okay, and these are my two columns. One is X and another one is Y. Okay, so this is the dependent variable and this is my independent variable. So when you have one single independent variable and one single dependent variable, then what you can call? You can call it as a simple linear regression model. So this is nothing but a simple linear regression model. For example, I have some kind of data points like this. In my X column, I have 1, 2, 3, 4 or 5 or something. Okay. I'm just taking this data set as an example. Okay. So this is not a real kind of data set. And now in my Y column, I have some kind of data points like 20, maybe 30, 40, 50, or 60, like this. Okay. So now, okay, so when you plot this particular thing on a kind of graph, like structure like this, for example. Okay, so when you plot this, for example, this is the x-axis and this is the y-axis, right? For example, uh, so when you plot this 1 comma 20, so what happens? So this is the 1 and this will be the 20 here. Oh, this will be the 20 here. Okay. And 2 comma 30, then what happens? This will be the thing here. So likewise, some kind of points, you'll get some kind of points like this. And this would be our model, that is nothing but the best fit line. Okay, let's imagine this. And now, so what is this particular thing? This is the best fit line. And how can you write that particular best fit line mathematically? So you can write that as y hat is equal to mx plus c. Okay. So when you compute this, so let's imagine you have got something like this. For example, y hat is equal to let's say some 29.5 x plus 50.96. Okay, you have got something like this. So what does this equation is actually explaining? You need to understand this right now. So what are these values actually? What is mean by this 29.5? What is mean by this 50.96? You need to understand it now better. Because just look at here, that is y hat equal to mx plus c. Just compare this equation with the values here. So what you will get when you compare here? You will get to know that m is equal to 29.5 and c is equal to 50.96. So what is meant by c here? C is nothing but our intercept, right? So this is our intercept. And what is meant by m here? This is nothing but the slope here, or you may call it as weight, or you can also call it as coefficient parameters, right? Okay, so what you can call it as c, you can call it as the intercept here. You can call it as the intercept here, or you can call it as the bias here. Okay, so this is the thing here. So, but what is mean by this? Okay, mathematically, you have already got to know that m is nothing but the slope, and m is nothing but the weight. C is nothing but the intercept. Okay, but conceptually, what exactly mean by these slope and intercept? Now I'm gonna tell you. For example, see here. So just look at here. So what is the value of m here? 29.5. So this is nothing but the slope, right? So this is actually saying for 1 unit increase in the x value, okay, for 1 unit increase in the x value, the y increases by 29.5 times. For example, let's take this as y. So for 1 unit of increase, so for 1 unit increase in the x, then the y will increase to 29.5. So this will be the, so this will be the meaning of this slope, right? But what is mean by the so it's actually, it's not actually increasing. It's just actually meaning the change here. For example, if x is increased by 1 unit, then it will also increase by, the y will also increase by 29.5. For example, if the x is decreased by 1 unit, then what happens? This 29 point, the y will also decrease by 29.5 times, right? So that's the thing here. And what is meant by this C here? C equal to 50.96. What do you mean by that? So you can describe the C as, for example, I'll draw a new graph here. So okay, so this is the X, right? So this is the Y. Okay. So uh, so what is meant by this intercept here? Our intercept is nothing. The intercept, that is this particular value 50.96, is nothing but what will be the value of y when all the inputs are actually 0. So what does that mean? That means when all inputs are 0, means x equal to 0, right? What will be the y, value of y? What will be the y value? So this is nothing but the intercept, right? So when x is equal to 0 means this will be the 0, right? So when x is equal to 0 means, so this is the here. So when x is equal to 0, uh, the intercept would be, that is the y value would be 50.96. It's actually saying. So then you can call it as for example, you can say for example, what is the 50 here? So so this is not the, actually this is not the meaningful value here. Why? Because when all the inputs are 0, how can the y value will go up to here? That is the 50.96. When you call 50.96, this would be the approximate 50.96. Okay. If all the x's are 0, then how should this particular value will go to 9.56 at this particular point? So this is not a meaningful pattern. I mean, this is not the meaningful value. But for the convenient purpose, I have taken this value as, let's say, 50.96. You can take whatever maybe. For example, I may take like, okay. For example, I'll take some 2.59. Okay. So our intercept would be 2.59. So what happens? So what happens? So 2.59, that is when all our x's are 0, our intercept would be 2.59. So let's say this will be the 2.59. So this is the 2.59 value. So our intercept would be 2.59. That means our best, that means our best fit line will usually pass through this particular point here, right? So this is the meaning of the intercept here. So this particular point where our best fit line is actually cutting here is nothing but the intercept, that is our C value, that is 2.59, right? So that's the thing here. So mathematically you can call it as what is meant by an intercept. Intercept is nothing but that's our best fit line, where our best fit line actually cuts the y. Okay, so this is the best fit line, right? So this is the best fit line. Intercept is nothing but when the best fit line cuts the y-axis at a particular point, that particular point is nothing but the intercept. So that's the technical kind of a definition. But when you want to look at what is exactly an intercept is, then you can say that when all the inputs are 0, that is when x is equal to 0, what will be the value of the y? That would be the perfect conceptual definition for the uh, term intercept. Okay, so that's it. Okay, so it's actually okay, you have already understood that. So did you get this particular point? That is what is meant by m. M is nothing but not in see, this is not the increase here. Actually, m is nothing but for 1 unit, change in x, what would be the change? What would be the change in y? So this is the thing here. For example, here I have, let's say, I have 1 unit of x has been increased. Okay, 1 unit of x is increased. Okay, then what happens? Then that implies y will also increased by 29.5 here. Why? Because this is the value of the m, right? So our y will increased by 29.5. If if 2 units of x is increased, then what happens? 29.5 plus 29.5. So that would be our, let's say, uh, that would be the value of our y. Did you get that? So for 1 unit of x, whether it is increased or decreased, whatever may be the thing is, it should apply the same for the y also. For example, here the 1 unit of x is increased, right? So instead of increased, what can I say now? For example, if 1 unit of x is decreasing, right? 1 unit of x is decreasing, then what happens? Y equal to y, the value of the y will also decrease by 29.5 times, right? So it will decrease, actually. This is not the minus here, but it will decrease. It will decrease by 29.5 times. Okay. So this is the thing here. So, uh, okay, by this you have got to know what is meant by the slope and intercept, right? So, but when you look at here, this you have only one kind of a independent variable, that is a single variable, that is x, and you are actually predicting one variable, that is y, right? So this is a simple linear regression model. But what happens when it is some multiple, when the data set has multiple kind of variables, what happens? I'll tell you. Okay, so for example, I have some kind of data set like x1, x2, and x3, and so on xn, right? So these are all my independent variables. Okay, and I also have one kind of a output variable, that is y, let's say. Okay, it has some kind of points, here, like this. So when you plot this on a particular plot here, what happens? So this would be the x1, right? So this would be the x2, right? So this would be the x3, and so on. Okay, so this would be the y value here. So whatever may be the relationship between all these independent variables and the dependent variable should be the form of, that's not a kind of a linear line here. So that's not a simple straight line, that's more than a straight line, which is nothing but some kind of a, in the form of a parabola here. So parabola is nothing but, see, this kind of a form, right? So this is a kind of a bowl-like form here. This will usually get formed when your data has multiple kind of independent variables and one dependent variable, right? So I'll talk more about this parabolic form later, but for now, what you can do is you can just look at this equational form. That is, we all know that y equal to mx plus c, right? So this is a simple straight line. I mean, simple linear regression. This is the simple linear regression. But what is this y equal to m1 x1 plus m2 x2 plus and so on plus mn xn plus c plus e. Okay. So what is it actually? So what is it actually? So see here, here we have x1, right? So this is x2 and so on. We have till xn. So there are so many kind of independent variables, right? So for each of the independent variables, we have uh, one particular weight, that is m1, m2, and so on, mn. So these are all the weights that belong to the particular, I mean, that usually explain each of these independent variables. So m1 explain about x1 and m2 explain about x2 and mn explain about xn. So all these weights explain, uh, I mean, corresponding independent variables, right? So this is the thing here. So now what happens is, so we everybody knows that we have two kind of an equations. That is, one is an actual equation. So for example, this is an actual equation, right? So what would be the prediction of this? Y hat equal to m1 x1 plus m2 x2 plus and so on plus mn xn plus c. But if you ask me, what about e? What about here? Can't we write e here? No. Why? Because we should not, I mean, there will be no e here. E is nothing but, what is this e here? E is nothing but the error, right? So there would be no e here. We only have uh, the weights here, that is the slope, and the independent variables here, and finally the intercept here, right? In the prediction, in the predicted model, that is in y hat, we don't have any kind of I'm writing here, in y hat we don't have any e, that is error, right? So we only have e in the actual thing, right? So in the v, sorry, in the y, that is m1 x1 plus m2 x2 plus and so on plus c. For such a kind of thing, we usually have this term, that is the error term. Okay, so that's it. Okay, so now, so okay, so what you can call this particular c? C is nothing but the intercept, or how do you call this? Intercept, or you can also call it as a constant also, right? You can also call it as a constant. See, I'm writing here. Now, what you can call this e here? So e is nothing but the maybe residual error or unexplained variance. Okay, or you can also call it as not unexplained, I mean, you can also call it as residual error, unexplained variance, or you may also call it as the difference between y and y hat. So you can also call it as the difference between y and y hat. So So this is the thing here. And just remember this. So this is the y here actually, and this is the y hat here. So these two are different. So this is the actual one, and this is the thing. This is the predicted one, which is predicted by our model here. So the both the different. I mean the difference between these two is nothing but the error, right? So that is the error term. So if you mention error here also in this particular equation like this, for example, plus e, then what happens? The difference, there would be no difference between this actual and the predicted one, right? So this would be the wrong case here. So you should not, you should never mention error in this particular y hat term, right? You only need to mention error in actual term, that is y. Okay. So now, in the simple linear regression part, I have explained that one unit of x is, if one unit of x changes, then what will be the amount of y that changes. I have explained here. So how do I explain this equation right now? That is, I want to explain this m1, m2, m3, and so on. So what I can do is, I'll just simply say, for example, if I consider this particular point, that is x1, so what happens for, for one unit of, so for one unit of x1, what will be the value of, y? This is the question. But here we have one condition, that is keeping all other things constant. So what does that mean actually? So what does that mean? So we are actually saying that when x1 is increased, I want to know whether, I mean, for how many times does this value of y has increased or not. I want to know this, but keeping all these other factors constant, that is m2, x2, mn, xn, all these will be, plus intercept, all will be kept constant. Okay, we are only interested in when one unit of x increases or decreases. So what would be our value of y? So for example, let's say, so I want to know for the another thing, that is another variable, that is x2. So I want to know for one unit of change in x2. So what would be the value of y? What would be the value of y keeping all other things constant? So this is the thing here, right? So this is about the multiple linear regression. Why? Because we have multiple independent variables, that is x1, x2, and so on, xn, right? But here we have only one kind of a difference here. Why? Because the difference is, for example, see here, when you look at this particular graph here, the best fit line is nothing but a straight line, right? Why? Because we haven't squared anything, right? See, the thing is here is, the difference between the y and y hat is nothing but the error, right? So when you calculate the difference between actual and the predicted one, you will get the error also, right? So this is only applicable when it is of simple linear regression model, right? But here, this is not the case here. Why? Because you have too many variables, and if you just consider this only y minus y hat, so what happens? You will need to sum up all the things. Okay. For example, you have calculated y1 minus y1 hat here, and you will add up y2 minus y2 hat here, and you will add up and so on plus yn minus yn hat here, right? So what you will get, all the plus and minuses will get cancelled each other, and you will left with the value that is 0. That means there is no kind of information that is left inside this particular value that is 0. So it should not be the case. So yesterday I have already talked about this particular thing, right? So all the things will get cancelled 0 and cancel each other, and you will get the 0. So that should not be the case. So how to avoid this kind of a situation? So it's, I mean, to avoid this kind of a situation, what you can do is you just need to square it up. For example, y1 minus y hat whole square, and you will add it up, y2 minus y2 hat whole square, plus and so on, plus yn minus yn hat whole square, right? So this is the thing here, right? So this is the thing here. So what happens is you will square all the things here. I mean, you'll square the error terms. Basically, this is nothing but the error, right? So the difference between y1 and y1 hat is nothing but the error. So basically, instead of just adding up all the errors, that is some of the errors, you are actually squaring it up, right? So now this will becomes what you can call it as, the whole thing is actually now became sum of squared error, right? So this is the sum of the squared error. So now further what you can do is you will just divide this sum of the squared error divided by n. So this in turn now has become mean sum of squared error. So mean SSC, this has become now like mean sum of squared error. So we will just use to plot all the independent and independent variables now on a graph like this here. So we will try to plot all the things here, right? So you try to plot all the things, and you will have the multiple kind of variables here. Okay, so when you try to plot this on a so this is the y here, this is x1, x2 and x3 here. So when you try to plot all these values, you will get a kind of a parabolic shape here. You will get a kind of parabolic shape. So what is this parabolic shape here? So this is a kind of a bowl like shape. Okay, so this will be the shape here. And now what is the situation here? So okay, I'll explain you instead of this instead of drawing these, I mean, instead of making it very complex, I'll try to explain it in a more reality manner. See here, for example, this is the equation y equal to m1 x1 plus m2 x2 plus m3 x3 plus and so on plus mn xn plus c. Okay, this would be the equation here. So what happens? So what happens here? Here what are the parameters here we have? That is, we have m. Okay, in general I'm writing m instead of writing m1 m2 m3 and so on mn. I'm just taking it as a in general m, and also I'm taking this as this intercept c, right? So I have m c, and I also, when it is this when it is the prediction here, that is y hat, if it is y hat, you will also have this particular sorry, no, in the prediction you won't have this. In the actual thing you will have this error, that is plus e. Okay, so you have the three terms m c e, that is the slope, this is the intercept here, and this is the error term here. So when you try to plot all these things on a particular kind of a graph, So what happens? So so this is this is the M here, and this is the C here, and this is the E here, right? So what you will get is you will get a kind of a parabolic shape, that is this kind of a shape. So this is the kind of a shape here. So now what happens is, uh, so with the help of this M and with the help of this particular C, you can try to achieve the best fit line, right? So for example, you'll have infinite number of lines or infinite number of shapes here. So what you can do is, by controlling, okay, by controlling M and C, you will get the best fit. You'll get the best fit line here, right? So you'll get the best fit line here. So how to do that? For example, actually you can tell me that this is not a line. So how do you say this best fit line? So okay, no worries. I'm just saying this is as an as in the sense of simple linear regression terms. Okay. So no worries. You will get the best fit model. Okay, you can call it as you'll get the best fit model in this. Instead of line, you can think of a best fit model. Okay. So if you want to have the best fit model, what you can do is you need to have the best M and you need to have the best C. That is the optimal M and optimal C here, right? So for example, what happens initially, our aim is to find the optimum M, that is optimum M, that is let's say this particular value. Let's imagine this is an optimal M value, right? And let's say this would be the C here, optimal C value. Okay, just think of this. Just think of like this. So this is the optimal C and this is the optimal M here. So how do you get that? How do you get that? I'll tell you. So what happens is, when you first start the linear regression algorithm, the linear regression will usually assigns us some kind of random values for M and C. For example, if I take this parabola here like this, see here, this is the parabolic shape. Ignore my drawing skills, just focus on the content here. So for example, this would be my random M value, and let's say maybe this would be my random C value, right? So it will actually assigns M value and the C value when we try to run this linear regression randomly. Okay, so it will assign these values randomly. Then what happens is, it will uses this linear regression model uses gradient descent method here, right? So what is meant by this gradient descent method? This is actually based on uh, a mathematical technique, a math technique. So what is the technique here? That's the most important technique here. Nothing but the partial derivatives. So the gradient descent method will usually runs on the basis of this particular principle, that is partial derivatives. So the linear regression will usually uses this gradient descent method, which in turn which is actually running on the principle, that is partial derivatives. What happens is, this gradient descent will automatically will automatically finds the best M and best C for us. Okay, which in turn gives the least least mean least mean sum of the squared error. Did you get that? So this is the thing here. So what happens is, just look at here. In this particular figure, what has happened is, linear regression has already initiated the random values for each of the M and C. Okay, but now and then what has happened is, I'm just drawing an arrow here. So the linear regression has already used now used a gradient descent. So what will happen now? So the gradient descent now the gradient descent now, it will usually brings down this particular M value towards the possible minimum here, right? When you look at this particular graph here, so this is the graph here, right? So it will usually brings down the value of M to the nearest possible distance of the M here, right? So this is the M axis, right? This is the axis of the M, and this is the axis of the C here. So what is the possible minimal distance uh, of the M here? So if this point will move to here, then the distance, so this distance would be the minimum, right? If the M moves to here, what happens? The distance here would be somewhat maximum, right? So it would not be the case like here. So our gradient descent algorithm will usually automatically detects this M value, and it will automatically brings down to this possible nearest position. This particular position is known as optimum M, or you can call it as best M, right? And now you will also have this particular value, that is the C, right? So it will automatically will goes to the possible value, that is let's say this particular value. Okay, so it will reaches to this particular point, which is nothing but the possible minimal distance here right now. Okay, so this is, I'll tell you regarding this particular topic in very much detail. So just this is just a brief kind of a brief kind of a description about the gradient descent working process, right? Just focus on here. So this C point will usually move to the possible nearest distance between the C here. So what happens is, so now what you can do is, so actually, so this is not the case, I think. Why? Because I mean the diagram itself is not so good, I think. So what can I do is, what I can do is, I just simply rub it all of these things, and I'll try to draw somewhat with neatly some kind of, see. So this is the perfect diagram, which is actually our linear regression assigns M value and the C value randomly. And now what happens is, we will get uh, okay. So we need to name it. So this is the error here. So this is the error. What is the error? What does that mean? Error is nothing but the actual minus predicted one whole square. So this is the sum of the squared errors, right? So this would be our intercept, that is the C, and this would be our axis, that is nothing but the M here, right? So now what happens if the gradient descent algorithm, if the linear regression uses this gradient descent, what happens? We will get some kind of parabolic form like this. Okay, so this is a kind of a parabolic form like this. So now we have the point of M here, right? So M point. So this is the M point here. It will automatically goes down to the possible nearest distance towards the M here. So this is the possible nearest distance. So this point is known as the optimum M here, right? So this M will goes on to here and it will get the optimum M. And now we have this particular C value, right? So the C value here, right? So this C value, what happens is it will usually goes down and it will reach some kind of a point here. Let's say the point here, right? It may reaches to the point here. So it is the possible nearest distance here, right? It is the possible nearest distance here. So this is the C here. Okay, so this would be the case. Now, what you can call this particular point, that is optimum. You can call it as optimum C here, right? So this would be the usual diagram. Okay, so I'll explain in greater detail in further videos, but for now, just look at some kind of points here. So the point here is the absolute minima is not equal to 0. See the minimum here, right? So this optimum M value will not be equal to 0, but it is slightly greater than 0. See, I'm writing here. The absolute minima is not equal to 0, but slightly greater than 0. Okay, so what happens is any combo of M and C which gives us the error, is greater than the least error, right? So the possible combination, the best combination of the M and C will not be equal to 0. It would be definitely slightly greater than the 0, right? So that's the thing here. Okay, so this is the thing here. And now what happens is, see, I have already told you there are two kind of methods here, which is, I mean, how to find the best fit line, how to find best fit line or a model, best fit line or model. So there are two kind of approaches. First one is algebraic method, right? Algebraically also you can find the best fit method. This is also known as the OLS, that is ordinary least squares method, right? And another one is nothing but the gradient descent, which I have already explained you right now. But what do you mean by this algebraic method? I have already yesterday I have already explained that method, and that's not so scalable. That what does that mean? The term scalable. Scalable is nothing but when we have too many rows and too many columns in our data set, then this OLS method will usually take forever. I mean, very much time. It will take so long time to compute the results here. So that for that I can tell, so that's not so scalable here. So that's why, that's what the reason I'm just avoiding that particular method here. So I'll be explaining the gradient descent right now. Okay. So in short, you can call this particular entire theory. You can just simply explain the theory with the help of a simple equation, that is nothing but our prediction of y, that is the predicted y, is equal to optimum m into our independent variable, that is x, plus intercept, that is the optimum c here. So this would be the equation. Did you get that? So this is the thing. So what is this optimal M? That is this particular optimum M and optimum C. So these two optimum M and optimum C are actually learned from our data. Okay. So we are given a data set, and after fitting that particular data set to our machine learning model, then you can that our model will usually learn from the data that we have some kind of optimal M and optimal C at these particular points, right? So this captures the relationship between y hat and x. That is the what you can call. This captures the relationship between independent variables and the predicted one, right? So OLS method, I have already said that this is not the scalable one, and this is one of many methods. So I usually prefer gradient descent instead of going for the OLS regression, right? So yeah, this is the thing here. So I hope the concept is very much clear to you. And okay, I'll see you in the next video. If you have any doubts regarding this topic, just comment down in the comment section. I'll definitely reply you. So this is it all regarding this linear regression structure. That is the structure of a linear regression. Here I have already explained about the simple linear regression structure with the help of this mathematical equation, and then I have told you what is meant by a multiple linear regression, multivariate linear regression. The name itself is actually explaining multivariate is nothing but when your dataset has multiple variables in it, that is more number of independent variables, you can call it as a multivariate linear regression. And then here, when you plot all the points here in the simple linear regression, the best fit line would be a linear form. Like the best fit line would be in a linear, it's a kind of a straight line. But when you have more than one single independent variable, you will have definite number of, you'll have more independent variables. Then the form of the best fit model is nothing, is not just a line, it's more of a line. You can call it as a parabola. It's the form of a parabola. So the best fit line is in the form of a parabolic form. And now you have already explained this entire simple linear regression using the help of a one single line, that is y equal to mx plus c here. And now y minus y hat is nothing but the difference between the actual and the predicted model, which is nothing but our error, right? So here, when it comes to the multivariate linear regression, you can explain this entire model using the help of an equation y equal to mx1 plus mx2 plus and so on plus mn xn plus c, right? So this is the equation here, where m is nothing but the slope, x1, x2, and so on are the independent variables. C is nothing but the intercept or the constant here. So I have told you what is meant by slope. Slope is nothing but for 1 unit change of x. So what will be the value of y? Whether if the 1 unit increases in x, then automatically y will also increase by that particular value. If the 1 unit decrease in x, then the value of the y will also get decreased by that particular value. And I have already told you why we should not use the sum of the errors simply. Why? Because all may get cancelled each other and we will left with the value that is 0. So we should never just calculate all the sum of the errors. Instead, what we can do is we just need to square up the errors. What happens if we square up and add it up? We will get a reasonable kind of value here, so with which we can decide upon what is the best fit model is. And now I have already explained what's the working method of a gradient descent. Initially, when we try to run the linear regression, the linear regression will usually tries to initialize the values of m and c randomly. They may get uh, the values here, like m value will be here and c may be here also. Okay, there is not a rule that m should be here and c should only be here. No, that's not a kind of a thing. So it's it's just random, right? So linear regression will just assign all these values randomly, and then it uses gradient descent method, which automatically brings down the m value and adjusts the c value to the optimal positions. Okay, which in turn gives us the least which in turn gives us the least mean mean sum of squared errors. So if anything is actually giving us the mean sum of squared errors, then we can confidently say that this is the best fit model or best fit line or best fit parabolic form, whatever may be. But here we have some kind of conditions here. Conditions is nothing but there is a kind of principles here. Okay, so absolute minima, our absolute minima will never be equal to zero. It should always be greater than zero. This is the condition, right? It will not equal to zero, but it also slightly greater than zero, right? See here, if it is equal to 0, then we don't have any kind of error. But does that the case usually happen in the world? No. Why? Because whatever maybe the model is, we still have some kind of error in it. So due to that reason, absolute minima will never be equal to 0, but it should be slightly greater than 0. So we need to find such combinations of m and c, which in turn will gives us the least possible mean sum of squared error. So how to find the best fit line? I have already explained you the two methods. That is the algebraic method. For this particular method, I have already told you the formula in the part 2 video of the linear regression. Just look at, have a look at that video, and you will get to know why I have denied to explain this particular method. Why? Because this is scalable. It may take too much time to compute the things when your data set has too many kind of variables. But in rather than but unlikely here, the gradient descent will usually takes less time comparatively, and it will does the job done, right? So this is the kind here. This is the kind of a thing, and that's all for this now. I hope you have got the clarity regarding the topics of structure of the linear regression. Now I'll explain some of the topics related to the linear regression in my coming videos. So I'll see you there, you all in the next video. In my next video, just please hit the subscribe button if you really like my content, or if you really like the way of teaching that I usually do. Thank you so much, and yeah, good night, happy meal, take care, Jai Hind.